All right, let's take a look at parallel circuits. And here we've got a 5-volt source and a 5-volt source here. We got two resistors in parallel, 1K and a 3K. And obviously they're both seeing source voltage because the path for this 1K goes back to the positive and the negative, and the path for this 3K goes back to the positive and negative. So these are just loads, and it's just like in our homes or on our cars, everything's connected to the same source. So when we plug devices in our house, we're certainly not seriesing them, or we'd have to break a circuit and interrupt it and add another one. We're putting them in parallel, and we plug them into the wall, we're adding them to the source. Now, this is a DC source, but a source is a source, at least in this respect. So if you look, I've got an ammeter right here, and it's telling us it's 6.67 milliamps total. And this 1K is using 5 milliamps, and this 3K is using 1.667 milliamps for that total of 6.67. Now I've solved this circuit, and the parallel equivalent of a 3K with a 1K, and the way I solved this circuit is the same way we solve parallel branches, and you can either use the reciprocal formula or use the product over sum. I use product over sum in my head. And I just simply said 3 times 1 over 3 plus 1, which equals basically 3/4. And I knew that the decimal version of 3/4 would make it 0.75K or 750 ohms. So I just made an equivalent circuit. So as far as this source is concerned, when we're solving circuits, it has no way of knowing uh, that there's a 1K and a 3K out here. It just sees a 750 ohm load. Now, if we break it as it exists here, we can see the individual currents, but the source is just going, hey, I got a 750 ohm load on me, and that's why I'm pulling 6.67 milliamps. So this is why we solve circuits down, and this is how we can also know that the sum of the current through this branch and the sum of the current through this branch equals total current, which is right here. So it gets to this point right here, and it goes, hey, part of us are going to take that path, and part of us are going to take this path. And so wanted to show you that, and then we'll show you how you can um, completely do Ohm's law for this. So obviously, if we're using Ohm's law, and parallel makes it a little easier when you're given resistance and voltage. So it's V I times R. So same thing we're used to using. Excuse me. So this is obviously 5 volts. I'll draw that in. And this is obviously 5 volts, same source. So we have our V and we have our solved R of 750 ohms. And we can come up with total current, which we've got it right here. So if we say V, which is V over R, that's going to equal 5 volts over 750 ohms here. So 5 volts divided by 750 ohms, if we break out our handy calculator, create me a pin to taskbar for that so I don't have to keep looking for it each time. There we are. So we'll kind of move this over here, and we'll say 5 divided by 750. We know the answer, but we're proving it. So this is in amps, but if I move it 1, 2, 3, I get 6.6666 continually, or 6.67 milliamps here. So I can come out here and say equals 6.67. And again, I'm drawing with the mouse, so sorry for the elongated 7, but it works. Now, the other thing we can do is we've got 5 volts across a 1K. We can do that math easy, because if we want to calculate individual currents for these, we can cover up the I. That'd be V divided by R. So it'd be 5 volts divided by 1K for this path, and 5 volts divided by 3K for this path. So this one's easy. It's going to be 1 milliamp, and it's milli because we're really dividing 5 by 1,000. We would get, excuse me, I said 1 milliamp. I meant 5 milliamps. Shame on me. I was trying to be swift. I meant 5 milliamps, not 1 milliamp. Because 5 divided by 1 is 5, and because it's millis, 1K, we're going to be dividing 5 by 1,000. We'll come out with 0.005 or 5 milliamps. And we're going to do the same thing over here. We're going to divide 5 by 3, and we're going to come out with 1.67 milliamps. And again, that's 5 volts divided by 3K or 3,000, and that's why we get that. So let's look at these on the calculator so you can see what I'm talking about. So we'll first kind of get this where you can see it, at least. So we'll say 5 divided by 1,000. And this is why we use these units, because I would have to write 0.005, or I can move that decimal place over 1, 2, 3, and we would have the 5 milliamps that we've got here. And now I'm going to take 5 and divide it by 3,000, and we've got 0.00167, or I move that decimal 1, 2, 3, that puts it right here, 1.67 milliamps. So again, that's why we use these. So we've solved that down. We can add these two together, and we would have total current 5 milliamps plus 1.67. Never hurts to use the calculator, but I can do this in my head. 1, because I can cheat and look up there, and 2, just because 5 plus 1.67 equals 6.67 milliamps. So that is a simple parallel circuit solved down to its equivalent circuit and proving Ohm's law both ways. And the reason these are seeing 5 volts is just because the top of this resistor is connected to 5 volts and the bottom of this resistor is connected to 5 volts. Same thing here, top is connected back to 5 volts, bottom is connected back to 5 volts. We could literally draw a source, and it could be 5 volt source, just like this one is. And we could hang as many resistors in parallel off of this 5 volt source, and they're all going to be seeing 5 volts of potential difference there. So I know I'm not drawing straight. Again, I'm not mouse talented, but you get the idea. Each one of these resistors, no matter their value, is seeing 5 volts. And it would just be a matter of dividing that 5 volts by whatever their resistive value is, getting each individual current and adding those. So parallel has some unique things about it, and I actually like working with parallel in some ways better than I do series. So hopefully this clears up some things for your parallel. But as we always say, if you have questions, please let us know.